Hello, mis amigos, and welcome back to the Valiant Swabian. Today we're gonna take a look to this problem 14, and it's kind of similar to the problem 12 or 13, I remember. And again, a little bit of geometry is gonna be applied. And it says a charge of 6.15 millicoulombs is placed at each corner of a square, 0.100 meters on a side. Determine the magnitude and direction of the force on each charge. So this is basically what we have here. We have a square and each size measures 0.1 meters. So we know that all of them are equals in charge. They are all positive, and you know what that means. That means that they don't like each other. They're gonna be rejecting their neighbors because they have the same polarity. So if we take a look to this particle, it's gonna feel a force coming from this other particle. It's gonna push it away. At the same time, this particle is gonna push it vertically, and this other is gonna push it horizontally. So it's very easy to see the direction of the resulted force. It's gonna be along the diagonal. Remember, the forces are vectors. So you can gather this vector, and you can make a new one. And it's gonna be pointing along the diagonal. Plus this vector with the same direction. So you can see that the final force is gonna be kind of this. And for this particle, the resultant is gonna be again along the diagonal because they're all equals. We're gonna have some symmetry, and same for this, going this, and for this one. Okay, they all have also the same magnitude. So the final force I'm gonna call it F net, or the net force. Is gonna be equals to the collection of all forces from the other particles. And let's put some names on this. This is particle 1, particle 2, 3, and 4. Okay, from equals 1 to 3. Because why not 4? Because this particle is 4, and this particle is not gonna exert any force on itself. So that's why we don't take it on account. Now this is gonna be equals to net force equals to F1 affecting 4 plus this. They are vectors, plus F2 affecting 4 plus F3 over 4. So let's calculate each of them. So F1 over 2 is gonna be only in the y-axis, and we're gonna use Columbus laws again. That says K times Q1, the charge of Q1 times charge of Q4 over the distance square, and that's gonna be vertically. So the Columbus constant is 8.9 times 10 to the 9, and the charges has the same value, which is 6.15 millicoulombs. So since they are the same, only in this case I'm gonna do this 6.15. So milli means 10 to the minus 3 coulombs, and since they are the same, I'm just gonna put a square on this charge value over the distance, and the distance between 1 and 4 is just 1.1 meters. From this to this is just 1.1 meters. So square 33 millions, or let's do this time to the 6 newtons, and that's gonna be horizontally in the y-axis. Now let's calculate the second force. F2 over 4 is gonna be again Coulomb's constant times the product between the two charges value, and they have the same charge, over the distance, and the distance is gonna be 0.1 times the square of 2, and all of this to the square. So if you don't buy it, well, let's just calculate the distance between 4 and 2. We're gonna draw a little triangles here real quick. This is 0.1, 0.1. So the hypotenusa is gonna be equals to what? To the square of 0.1 square plus 0.1 square. And since they are all the same, we can just say this is 2 times 0.1 square, right? So yeah, that's gonna be equals to square of 2 times square of 0.1 square. That's equals to 0.1 square of 2. That's why in any straight triangle in which two sides are equals, the hypotenusa is gonna be just the same value times square of 2 always. So that's gonna reduce time. So that gives me 16.8 millions or 10 to the 6 newtons. Okay, but we're forgetting the direction. So this is the magnitude itself going in this direction. So let's call this axis, let's call it like, I don't know, R. Okay? So this is going in the R direction. I mean, you can decompose them in X and Y, but we don't need to do that. You're gonna see it at the end. So let's calculate 3/4. Okay, but as you can see, 3/4 has the same value as 1/4, right? These two forces are equals in magnitude, but different direction. Why am I saying this? Because the charges are equals. The Coulomb's constant is not gonna change. The charges are equals, and the distance is still 0.1 meters. So the magnitude is 33.6 times 10 to the 6 newtons in the X direction. Now we're gonna take this force, and we're gonna group them. We're gonna make it just one force. So we have this and this. Now we're gonna make a little triangle. They're equals in magnitude, so the resultant force is gonna be just like this. So this is force 1/4, and this is force 3/4, right? So the resultant is gonna be this value again, because they're equals. This is exactly what happened with the distance in this triangle, because they're equal. This is a straight triangle, so this magnitude is gonna be 33.10 to the 6 square of 2. In what direction? In the R direction, because we just invented this name, the R direction, and that equals to 47 times 6, 10 to the 6. This is 47.6 times 10 to the 6 newtons in the R direction. So let's put a name on this. This is the force 3/4 plus 1/4, because it's the result from these two, all right? Now we have to gather this and this force, and we need to just make it one. So it's gonna be this value plus this value, and that's the final answer. And that gives us 64.4 times 10 to the 6 newtons in the R direction, following the diagonal away from the center of the square. What about the others? They have the same value, and the direction are following the diagonals, as we just said at the beginning. Okay, so guys, I hope that you understood this exercise. See you in the next video. Bye bye.